This video is brought to you by mywayteaching.com.
Let us solve one simple example. A battery of 10 volt and negligible internal resistance is connected across the diagonally opposite corners of a cubical network consisting of 12 resistors, each of resistance 1 ohm. Determine the equivalent resistance of the network and the current along each edge of the cube. So this is the question and this is the cube. See, the network is not reducible to a simple series and parallel combination of resistors. It's very complicated. So here, a clear symmetry in the problem which we can exploit to obtain the equivalent resistance of the network. What we have to do? Let us see what is the clear symmetry that we can do. See the paths A dash, the first one A dash, AD, this one AB are obviously symmetrically placed in the network A dash, AD and AB. Thus the current in each must be same, say I. So further at the corners A dash, B and D, corners if you consider A dash, B and D, the incoming current I must split equally into the outgoing branches. So in this manner the current in all the 12 edges of the cube are easily written down in terms of I. So using the KIRCHHOFF'S first rule and the symmetry in the problem, so let us first consider a closed loop, that is A, B, C, C dash, E, A. So this is the first closed loop. C dash, E and A. Okay, this outer part. So applying the KIRCHHOFF'S closed loop formula. So first this one, if you move from this direction, so if you consider this I, that is minus I into R, the current entering the node and current leaving the node. Then here minus 1 by 2 R into I, again here in this branch minus I R, and here negative sign first comes first, so it is plus epsilon is equal to 0. So R is the resistance of each edge and this one is the EMF of the battery. So this epsilon is equal to 5 by 2 into IR, and the equivalent resistance of the network if you consider, that is given by EMF by 3I, that is 5 by 6 into R. For R is equal to 1 ohm, R equivalent is equal to 5 by 6 ohm, and for EMF 10 volt, the total current is given by 12 amps. I is equal to 4 amps, isn't it? So the current flowing in each edge can now be read off from the figure, in this figure. So here it should be noted that because of the symmetry of the network, the great power of Kirchhoff rules has not been very apparent. In a general network, there will be no such simplification due to symmetry, and only by application of Kirchhoff's rules to junctions and even to closed loops we can solve the problem. Determine the current in each branch of the network shown in figure. So this is the branch. So here we have to determine the current in each branch. Each branch of the network is assigned an unknown current to be determined by the application of Kirchhoff's rules. So in order to reduce the number of unknown currents at the outset, the first rule of Kirchhoff is used at every junction to assign the unknown currents in each branch. Okay, that is, we then have three unknown currents, I1, I2 and I3, which can be found by applying the second rule of Kirchhoff to three different closed loops. Okay, so here first we have to assign currents to each branch, applying the first rule of the Kirchhoff. So here the current I1, and here it is the current I2, and here it is the current I3. So and here it is leaving the node. So obviously the current entering the node, sum of the current entering the node is equal to current leaving the node. So this will be equal to I1, this is leaving, minus I2, using the first rule of Kirchhoff, isn't it? So that is the first case. And here current I3 and here current I1 minus I2. So in this, here the entering the node is I1 minus I2, leaving it is I3. So it is I2 plus I3 minus I1. So using that, here current I2 is entering, current I3 is entering. So in this, the current is I2 plus I3. Okay. So here current I2 plus I3 is flowing along with this current I1, that is leaving the node. Okay. So here they have applied the Kirchhoff's first law in order to get the currents in each branch. Now we are going to apply Kirchhoff's second rule for the first closed loop, that is ADCA. First we are considering the loop, that is ADCA. A, B, C, A, this lower triangle. So we are moving like this, minus 4 into I1 minus I2 so here current is moving in this direction. So here if you consider plus, if you consider minus, so we are considering the loop in this direction, upper direction. So it will be plus 2 I2 plus I3 minus I1. Okay, and here minus I1 plus 10 volts is equal to 0. Okay. Now if you consider the closed loop ABCA, we are moving like this. So again first is minus 4 I2 minus 2 I2 plus I3 minus I1 plus 10 is equal to 0. So for the first loop, if you simplify for this loop, we get the equation that is 7I1 minus 6I2 minus 2I3 is equal to 10. And if you simplify this second equation, we get I1 plus 6I2 plus 2I3 is equal to 10. Okay. Now if you consider the third loop, that is BCDEB, then we'll get 5 minus 2 minus 2 I2 plus I3 minus I1 is equal to 0. That is given by 2I1 minus 4I2 minus 4I3 is equal to minus 5. So now we got 3 different equations, isn't it? So the first equation was 7I1 minus 6I2 minus 2I3 is equal to 10. And the second equation was I1 plus 6I2 plus 2I3 is equal to 10. And the third will be 2I1 minus 4I2 minus 4I3. So if you solve these 3 equations, we get the value of I1 as 2.5 amps, the value of I2 as 5 by 8 amps, and the value of I3 as 17 by 8 amps. Okay. So the currents in various branches, if you consider, so the current in branch AB is I2, that is given by 5 by 8 amps. So the current in the branch CA, if you consider, that is I1, that is 1 by 2 amps, and the current in the branch DEB is I3, and the current in the branch AD is I3. The current in the branch CD is given by I2 plus I3 minus I1, which is gives 0 amps. Current in the branch BC is 2.5 amps. Okay. It is easily verified that Kirchhoff's second rule applied to the remaining closed loops does not provide any additional independent equation that is the above values of currents, they satisfy the second rule for every closed loop of the network. So if you consider the total voltage drop over the closed loop, BA DEB, if you consider, so BAD EB, okay. And in this case, so the total voltage drop will be 5 volt, pi by 8, which will be equal to 0. Okay, this proves this Kirchhoff's second rule.